Hello everybody and welcome to my 28th video. This is on the Quine-McCluskey procedure in quaternary. This procedure is based on the algebra of my 24th video, which is called a quaternary algebra with 3 binary operators, and all the circuits for the functions for that algebra can be found in my 25th video, binary implemented quaternary logic circuits. Right, so let's get started. First we have the unary operators of the algebra. Now a plus is a plus 1 modulo 4, a plus plus is a plus 2 modulo 4, and a minus is a plus 3 modulo 4. Minus 1 is the same as plus 3 modulo 4. So this is a plus, a plus plus, and a minus. So for example, 3 plus 3 is 6 divided by 4. Well, 6 goes into 4 once, remainder 2. So there's the remainder there too. These are the binary operators for the algebra. Binary in the sense that they require at least 2 inputs. This is the minimum of function shown here for 2 variables a and b. And this is the maximum of function shown here for 2 variables a and b. So the minimum of function just takes the minimum value of whatever is on its inputs. So the minimum value of 3 and 1 here is 1. The maximum takes the maximum. 3 and 1 here is 3. Now this is the ampersand function. This is a 2-input function only, and it's non-commutative, so it matters which input is y and which input is x. For example, y equals 0 and x equals 1 is a 1, but y equals 1 and x equals 0 is a 2. Did I say that right? Y equals 0 and x equals 1 is a 1, y equals 1 and x equals 0 is a 2. That's right. So we can split these up into 4 tables, A, B, C and D, and these are just taken from x ampersand y. So I'm going to use table A in the examples of the Quine-McCluskey procedure in quaternary, because it represents a sum of products and a product of sums expression. So I'm going to use this coding here in the next table. Right. Now this is a table of 3 variables a, b, c. F is here 0, 1, 2, 3, and y and x are coded as in table A in the previous example. So x can assume the value of 0, 1, and r here is for 0 or 1, and y can assume the value of a 2 or a 3, and r here is a 2 or a 3. So you've got f equals 0, 1, 2, 3, and x. X is a don't care state, which can assume the value of 0, 1, 2 or 3, and r is, like I said, accordingly valued. So we list the values of a and b and c as you would a normal truth table. 0, 1, 2, 3 and the pattern repeats. 4 zeros, 4 ones, 4 twos and 4 threes and the pattern repeats. 16 zeros followed by 16 ones, 16 twos and 16 threes. And the value of n is the quaternary equivalent of a, b and c. But you don't have to worry about that. You just list the truth table as you would normally, and then list n from 0 down to 63. So for example, 12 would be 3 times 4. Let's pick another one. This is the units column A. This is a 4 column B. This is a 4 column C. 16 column C. Another column would be 64 if it was D. So 20 is 1 times 16 plus 1 times 4, say. So 16 plus 4 is 20. Right. So I've coded f. F is I've just chosen a random function of f well, not random, but carefully chosen to demonstrate this example. And x and y are the values corresponding to f here and here, x and y here and x and y there. Okay. So this is function y of the previous truth table, and this is a table of the logic 3's for which y equals a logic 3, and it's a sum of products expression I'm doing. So we'll list all the values here for which n equals a logic 3, and we'll list the values of a, b and c here. And what we do is we look for a common logic state of 0, or 1, 2 or 3, and then one variable varies by 0, 1, 2 and 3. So we can see there's an example here of 4, 5, 6 and 7, 4, 5, 6 and 7. C is a 0 in all cases, so C there is a 0 there. B is a 1 in all cases, so B is a 1. And A varies by 0, 1, 2 and 3. So you represent that with a dash to say you've cancelled out that variable. So you do that for as many times as you can. Look for all the variables the same logic state except for one which varies by 0, 1, 2 and 3. And you reduce it as much as you can. So these are the redundant states, and you don't list these in here. You keep them separate, and you can combine them separately. For example, 32, 33, 34 and 35 here is there, and this is a 2, so C is a 2. This is a 0, so B is a 0, and A cancels out 0, 1, 2, 3. A cancels out there. So you do that for the R's as well as the logic 3's. So here we have C equals 2 and B and A cancel. Here this is C equals 2 and there, and B equals 0, 1, 2 and 3, so B cancels, and A is a dash anyway, so A just cancels to a dash. So this is a two variable table, either AB or BA or BC, and this is a one variable, either CB or A. Right, so this variable has 4C has 16 n values attached to it, and this variable here, these two variables, have 4 n values attached to them, each one. Right, so what I'm going to do is I'm going to show you how to turn these into an expression. Okay. So here is a logic state table and a variable table. If the logic states are 0 in the previous table, the variable's x minus. If it's a 1, it's x plus plus. If it's a 2, it's x plus, and if it's a 3, it's x. So this is the prime implicant table, and what you do is you assign variables here. These are the minimum of terms, a plus plus b minus c, a plus plus b c, b plus c, a b plus c plus, and a plus b plus, a plus and b plus, or min b plus. So these variables here are the n variables and values for all of which the function y equals a logic 3. So if I just put that, these are all these values here, and these variables are labelled according to the numbers which are in this table. For example, b equals 1 and c equals 0. b equals 1 is x plus plus, so that's b plus plus, and c equals 0 is x minus, so that's c minus there. So that expression would be b plus plus and c minus. So the idea of the prime implicant table is to find the minimum coverage of all these n values with a logic 3 for the minimum amount of terms in here. So a plus plus b minus c plus plus covers a logic 3 at n equals 17, for example. Obviously, the less number of variables there are, the more n values they cover. So what we do is we look for a column with only one x in it, and that term is denoted with a star. These are prime implicants, and the ones with the star are essential prime implicants. They're the ones that we have to include in the final expression for y, which is here. So it can be seen that the ones there, so one there, one there, so that becomes an essential prime implicant. A one there, that becomes an essential prime implicant, and similarly for all the others, except for this one. This one can be deleted because 42 this only covers 42, but 42 is covered by C plus, so this is redundant. You can delete it, denote that by an x. So the final expression for y is a plus plus min b minus min c plus plus, which is this one. A plus plus min b min c, which is this one. Max b plus plus c minus, which is this one. Plus max a min b plus, which is that one. Min c plus, which is this one. And you add a constant logic state to the expression, which is a quaternary logic 2, to make it 2-valued. So this is the expression for y. Right, now we're going to do the expression for x. This is a product of sums expression. You take the maximum of function terms and connect them together using the minimum function. So these are all the values of n for which x equals a logic 0. Here a, b and c are as before, and again I forgot to mention before, once you've combined variables of n, once you've done that, you check it with a check mark, and only the unchecked variables go into the prime implicant table. So here we have a, b and c, n values, and if we can go 0, 4, 8, 2, 0, 4, 8 and 2, that's these three, sorry 12, 0, 4, 8 and 12, there, that's a 0, which is a 0 there, that's 0, 1, 2, 3 on b, so b is a dash, and a is a 0 in all four cases, so that's a 0. So you do that as many times as you can, and once you've used the term, you check it off, and only the unchecked terms go into the prime implicant table. These are the redundant states, the r's. So there again, so it's 32, 30. This is the same table as before for the r's because it's the same one for x and y with regard to r's. So 32, 33, 34, 35 is here. That's a 2, c is a 2, b is a 0. Yep, b is a 0, and a cancels out to 0, 1, 2 and 3, so it is a dash. And that's the same for this one as well. So we've got a single n values for here for 3 variables, 3 variables, and 1, 2, 3, 4, 5 two variables. If you can't, you stop once you can't combine any more variables. That's it. So we'll look at the primary implicant table. Here these are logic states again as before. Different coding of variables. If the logic states are 0, it's x. If it's a 1, it's x minus. If it's a 2, it's x plus plus. If it's a 3, it's x plus. That's because you're dealing with the logic zeros. And the primary implicant table is before, so if we can look at here, 24, C is a 1, B is a 2, and A is a 0. B is a 1, A is a 1, sorry, which is x minus. Have I got that right? B is a 2, it's x plus B plus plus, and C, so A, sorry, C is a 0, so it's 0. Yeah, so it's C minus 0. Sorry, C is a 1, so it's minus. B is a 2, so it's B plus plus, and A is a 0, so it's x, so it's A, sorry, right. So A, B plus plus max, A max, B plus plus max, C minus has an n value of 24. A max B plus has a value of 44, and you do that for all the values of x, values of n, sorry. So when a term covers a value of n, you mark it with an x in the column that it denotes. So again, the idea is to cover all the values of n with the least amount of terms as possible. So again, you look for a column with one x in it, and that denotes an essential prime implicant. These are prime implicants. An essential prime implicant has an x in one column only. So you can see here, there, that's an essential prime implicant, and there. But here, you don't delete them because there's no other x's in the column, but you have a choice. You can either use A plus plus max B plus plus or B plus plus max C plus plus. So the final expression for x is all these essential prime implicants here plus this one, which is here, A plus plus max B plus plus, and then again all these essential prime implicants here plus B plus plus max C plus plus. So you have a choice, and there. So this is A max B plus plus max C minus min A max B plus min C plus plus min A max C min A plus plus max B min B plus C minus min max A plus plus max B plus plus. And again, you add a constant logic state to the expression to make it two-valued. That's a quaternary logic one. So that expression, like I say, has A plus plus and B plus plus in it. The next expression is the same except it has B plus plus and C max C plus plus in it. Of course, F equals X ampersand Y. Right, I think that concludes the video. I'd just like to say I hope you've enjoyed it. Thanks for watching. Bye.